Cloud COVID-19 Research Award for the project of artificial intelligence based tools for COVID-19 detection in 2020, and he has received Young System Scientist Award in 2016 from System Society India. He has received PhD Research Fellowship from University of Antwerp, Belgium in 2009, and a Technology Breakthrough Award in 2007 for the development of Brain Assist, a state-of-the-art tool for brain tumor analysis. So Dr. Jenny Rajan's area of interest include image processing, medical imaging, and deep learning. So I request Dr. Jenny Rajan sir to take over. Thank you.
Yeah, thank you, Basiraj, and thank you, Sham. So good morning, all of you. So on today's lecture, I will try to discuss some of the basic concepts associated with the neural network. So today we will discuss how to build a neural network and how a neural network work. And in tomorrow's class, we will discuss what are the limitations of artificial neural network and how those limitations can be addressed with the help of a convolution operator. So I assume that most of you are familiar with the basics of machine learning. So if you look at this screen, you can see two objects, right? So there is a circle and there is a tree, right? So yeah, so assume that you want to write a program to identify these objects. Which one is difficult? See, you have to write a program to identify a circle and you have to write a program to identify a tree. Which one is the easy one? You can unmute your mic and you can respond.
Circle is easy.
Why that? Why dictating circle is more easier than dictating the tree?
It has a definite shape, and we can give all the characteristics of a circle by providing some information.
Okay. So you can
we
describe
define the equation?
Yeah, so you can describe a circle mathematically, right? So we know the equation of a circle. So you can use that knowledge to identify the circle, right? So if I ask you to write a program, so you will incorporate these knowledge in your program, and then you can easily identify a circle, right? So yeah, of course, circle can be of different radius, but that will not be a problem. So you can search for circles of different radius, and if there exists a circle in the input image, then you can easily identify it. What about the second object? So how will you identify a tree from a given image? Or what approach you will follow? The first approach.
Color.
But different objects can have the same color, right? So if you look at this image, the tree is of green color, but there exist other objects also of the same color, right? So with this color, how will you identify the tree?
You will consider the structure of the tree as well.
But that again is difficult. There exists trees of a different structure. Or how will you incorporate the structure into a program?
You have to extract the features which will distinguish the tree from other object in the scene.
So what kind of algorithms you use to identify a tree? So if you look at the first object, it is straightforward and easy, right? So we have a circle. You know the equation of a circle. Incorporate this knowledge into a program. Then it will work. So our program will read the input, and if there exists a circle, the program will give an output, right? There is a circle in the image. And the second problem is to identify a tree. You told that you can look at the structure, you can learn some kind of features from this object to see whether it is a tree or not, right? So what kind of program or what kind of algorithm you use to identify this object?
We have to provide a training data set, sir.
Yeah, that is a data set, but what about the algorithm?
Classification.
Sorry?
CNN.
So you use some kind of machine learning technique, right? So you use some kind of machine learning algorithm to achieve this task. So use an algorithm, ML algorithm, to develop a model. There exist different kinds of different ML algorithms. You can use one of those algorithms to develop a model. And what this model will do?
Sir, it will classify the, when we testing the data, it will classify the trees or which are not trees, the images it will be. Like that it will be going to predict them, sir.
So when you see, we will use some kind of machine learning algorithm. It can be a support vector machine, it can be a logistic regression, a neural network, or any kind of algorithm. So we use this algorithm to develop a model, and you can assume this model as a mathematical function that takes some kind of image as an input, and it will give some output, right? So this function will try to map the given image to a class. Say a class belongs to tree or some other class. You can assume it is 1 and 0. If it is 1, that means the input is a tree. If it is not 1, say if it is 0, the input is not a tree. This is what this model will do, right? So with the help of a machine learning algorithm, we are trying to develop a model that do this classification, right? So if you look at the machine learning algorithms, you can see that all these models or all these machine learning algorithms try to learn from the data. So if there is no data, then you will not be able to develop this particular model, right? So if you look at the first problem, you can see that you don't need much data. So you don't need data at all to develop to write a program to identify a circle. But if you look at the second problem, we need the data. We need a large amount of data to develop a model. And when we develop a model, so we develop a model with the help of an algorithm, with the help of a machine learning algorithm, right? So this machine learning algorithm, what it tries to do is to identify some kind of features that discriminate a tree from other kind of object. That is what we do with the help of a machine learning algorithm, right? So if we do not have enough data, then we will not be able to develop a model, or our model will not be that good in identifying a tree or not. So if you look at the literature, you can see that there exist a large number of machine learning algorithms. And in today's class, we will be focusing only on artificial neural networks. And you know that KNNs are considered as a popular machine learning algorithm, right? So we will see how can we develop models with the help of artificial neural network. Okay, so in this screen, again, you can see some different problems. So if you look at this screen, you can see 4 different pictures. So in this image, what we want to do is we want to identify all the circular objects. So in this case, we don't need any machine learning model because the object that we want to identify are of circular shape. So this can be easily coded in a program, and you don't need any ML model to achieve this task. And if you look at this this problem, so we want to count how many buttons are there. So if you look at the shape of the button, again you can see that all these buttons are of circular shape. So again, I will not go for a machine learning method to solve this problem. So since all these objects are of circular shape, I can easily incorporate this knowledge into a program, and I can write a program to achieve this task. But if you look at the other 2 problems, so in this case, what we are trying to do is to identify the face from an input image, the human face from an input image. So you know that it is very difficult to describe the face mathematically, right? So in this case, I prefer to use a machine learning algorithm to achieve the task. Because so in this case, see, when I use a machine learning model, that means I need I am using an algorithm that learns from the data, and we are trying to come up with some kind of a empirical solution, right? So to develop a solution, I need a large number of input samples. So with the help of a large number of face images, I will develop a model. And once I develop a model, the model will be able to identify a human face from an input image, right? So in this problem also, you can see we have an MRI image as an input, and we want to see whether there exist any abnormalities in this image, say tumor or not. So again, we have to train the algorithm to learn the characteristics of tumor. So if you compare these 4 problems, you can see that in these 2 cases, see, we don't need a large number of samples to develop a model. But of course, when we use a machine learning algorithm, you need a large number of samples to develop a model. Again, the number of samples is very important when we develop machine learning model. So if you do not have a large number of samples, then machine learning algorithms are not a choice. Right? If with very less amount of samples, it is very difficult to develop a model that performs well. Okay. So as I told earlier, as I mentioned earlier, artificial neural networks, especially convolutional neural networks, currently provide the best solutions to many problems in image processing, computer vision, and natural language processing. If you look at the literature, you can see that most of the problems in computer vision or NLP, the researchers use CNN to come up with a solution. Right, that shows how popular convolutional neural networks are. So these artificial neural networks or convolutional neural networks are built with the help with these artificial neurons, right? The artificial neuron is basically inspired by the working of a biological neuron. And in the coming slides, we will see how what are the similarities between an artificial neuron and a biological neuron. So as I mentioned earlier, so this artificial neural network it approximates a you can assume a neural network as a function that maps some kind of inputs to some kind of output, right? So in that sense, artificial neural networks can be considered as function approximation algorithms. So if you look at this figure, it shows the milestones in neural network. And in today's class, we will try to discuss some of the popular methods in artificial neural network, or some of the important papers in artificial neural networks. Okay, so before discussing artificial neural network, first I'll give a brief overview about neurons. So you know that artificial neural network is basically inspired by the working of a biological neural network, right? So this is the anatomy of a biological neuron or a nerve cell. So if you look at this nerve cell, see this is how a nerve cell or a neuron look like. So it has dendrites. These dendrites receive inputs from the sensory cells or sensory organs or from other cells, and this input will be processed in the cell body, the soma. And this processed input, it will be the result of the processed input, some kind of a signals will be communicated to the next nerve cell through the axon. So you can see that there is a covering over this axon. This is called myelin. This myelin will help in fast transmission of the processed data. And these neurons communicate through this synapse. So there is no physical connection between these two neurons. So the communication is it is something like electrochemical signals. That is how it communicates. There is no physical connection. So and this region is called the synapse. So this is how a biological neuron look like, and inspired by the working of a biological neuron, McCulloch and Pitts developed an artificial neuron. And with this artificial neuron, they developed a neural network, and that is what we are going to discuss today, the first paper. So their model was published in 1943 in a paper titled A Logical Calculus of the Ideas Immanent in Nervous Activity. This paper is considered as a classical paper in artificial intelligence and neural network. So we will see what are the contributions in this paper. So in this paper, they developed a mathematical model of a biological neuron. So you can see this is a model that they developed. So you will, and this is how a biological neuron look like. So you will see the similarities between a biological neuron and an artificial neuron, and how an artificial neuron work. So the biological neuron we already I already explained. So if you look at this artificial neuron, you can see that this artificial neuron can take n inputs, and associated with every inputs there is a weight. And this you can assume as the cell body. So in the cell body, what we do is we will compute the weighted sum. So for every input, there is a weight, right? So we will compute the weighted sum, and this weighted sum we will give to an activation function. And based on the weighted sum, this activation function will give an output. So this can be described like this. So first we will compute the weighted sum. See, we have n inputs, right? So we are going to compute the weighted sum. Sigma I is equal to 1 to n, I, wi. So these weights can be considered as equivalent to the synaptic strength in a biological neuron. So first we will compute the weighted sum. So once we have this sum, say we will check the value of this sum. If this sum is greater than a threshold, then the neuron will fire. Otherwise, the neuron is not going to fire. In this case, we are going to use a step activation function. So this is how the artificial neuron proposed by McCulloch look like. This is a very simple mathematical model of a biological neuron. So this model will take n inputs, and for every input there is a weight, and then we will compute a weighted sum, and based on the strength of the weighted sum, the neuron may fire or it may not fire. Right. So if you look at this model, you can see the parameters of these models are the weights and the threshold. So if you want to use this neuron to solve some kind of problems, then what we are trying to do is to come up with the appropriate values of the parameters. Okay, so any questions? Is it clear? Okay, so now we will see how can we use this McCulloch's model to develop a logic gate. So as I told, this model is very simple. It is a very simple mathematical model of a biological neuron. So you cannot simply compare the MB model with a biological neuron. The biological neuron is much more complex when compared to this simple mathematical model. So even though this model is simple, this model can be used to develop logic gates. So we will see how can we use this MB model to develop an AND gate. So here I'm going to use this MB model to develop an AND gate. Developing an AND gate in the sense I want this neuron to act like an AND gate. So you know the truth table of AND gate, right? So AND gate will fire when all the inputs are 1. Otherwise, the output will be 0. So this is what we want to do with this artificial neuron. So this is how my neuron look like. So this neuron will take 2 inputs, A and B. So associated with the weight of A is WA, and assume that the weight of B is WB. So then we will compute the weighted sum, and based on the strength of this weighted sum, the neuron has to fire, right? So output, the expected output is 1 or 0. So you can give the value A and B can take the value 1 and 0, right? So when we give 1 as input, this neuron should fire, and for all other combinations, the neuron should not fire. This is what we want to do. So we have to come up with the appropriate values of WA, WB, and T such that this neuron act like an AND gate. So we are trying to find the values of these parameters. So you'll take the first case when both inputs are 0. That means when A is 0 and B is 0, the neuron should not fire, right? That means when A is 0 and B is 0, output should be 0. That means the weighted sum 0 into WA plus 0 into WB, this value should be less than or equal to T, right? So when that means when both inputs are 0, this neuron is not going to fire. So that means 0 less than or equal to T, or T should be greater than or equal to 0. Now, when A is 0 and B is A is 1 and B is 0, in this case also the neuron should not fire. That means 1 into WA plus 0 into WB. This value should be less than T. That means the neuron should not fire, or WA should be less than or equal to T. Now we will set A as 0 and B as 1. So in this case also the neuron should not fire, right? Then you will get WB should be less than or equal to T. Now, when both inputs are 1, the neuron should fire, right? So that means 1 into WA plus 1 into WB, this value should be greater than T. Greater than T means in this case, we should get an output 1, or the neuron should fire, right? So we will get an equation WA plus WB greater than or equal to T. Now we have a system of equations here. We have 4 equations here. So you can solve these 4 equations to find the values of WA, WB, and T. Of course, here we have many solutions, but you can take any solution that satisfies these 4 equations. So now I am going to set the value of WA as 1 and WB as 1. So if you set WA as 1 and WB as 1 and T as 1.5, then this will satisfy all these equations, right? The t should be greater than 0. So I'm going to set the value of t as 1.5. WA should be less than t. So here I gave the value of WA as 1, that is less than t. WB also should be less than or equal to t. So here I give 1. And WA plus WB should be greater than t. So WA plus WB is 2, right? 2 is greater than 1.5. So these values satisfies all these equations. Now, if we if we substitute these values in this neuron, this neuron will act like an AND gate, right? But of course, as I told, different solutions exist. Whatever values that satisfies this equation will make this neuron act like an AND gate, right? So if you give these values here, if you set WA as 1, WB as 1, and if you set T as 1.5, then this neuron will work like an AND gate. So if you can create logic gates using neuron, then you can also create circuits or a computer using a neuron. This was the motivation to develop this model. So they were trying to develop a computers with the help of neurons. So as I told, see the concept is very simple. So this is a simple mathematical model that is motivated by the working of a biological neuron. But of course, even though this is very simple, you can design gates using these artificial neurons. So now I explained how to create an AND gate using McLaughlin model. You can also try designing other gates like OR or not using MB model. So again, if you want to use if you want to design OR gate, again you have to solve a system of equations and then you have to come up with the appropriate values of the parameters. Okay, any questions?
Sir, can I ask a question?
Yes.
Sir, you said that the data for movement of work, the data set has to be large. So
I am not able to hear you properly. Can you?
Sir, you said the data set has to be large for neural networks to work.
Sorry.
Sir, am I audible?
Madam, your voice is not clear.
Okay, sir, I'll ask later.
Okay, any other questions? Or you tell me, so I assume that you have some understanding about how MB model work. So what are the limitations of this model?
Excuse me, sir.
Yes.
So how we can decide the value of t?
The value of t.
Yes, sir.
Yeah, so you can find the value of t by solving the system of equations, right? So see how we design this AND gate. So we considered these 4 inputs, right? So based on these 4 inputs, so now we have a system of equations here, right? So if you look at this equation, you can see that when both inputs are 0, you will get this equation. So this equation says that the value of t should be greater than or equal to 0. So you can take any value that is greater than or equal to 0 as the value of t. But it should also satisfy the other conditions. So here we have 4 equations. So you can select a value of WA, WB and T that satisfies all these 4 equations. Is it clear? So here I fix it as 1.5. You can also select the value of T as 10 because 10 is also greater than 0. Then appropriately you have to select the value of WA and WB. Is it clear? Okay, so what are the limitations of this model? You can see, I think everybody is muted their mic. You can unmute the mic and you can, whatever ideas come to your mind, you can just speak. So what are the limitations of this model?
The results will be with respect to the weightage and the threshold, and it can be categorized only 2 classes.
I know that 2 classes that you can modify it, So for any machine learning model, what we are trying to when you train a model, what you are trying to do is to come up with the optimal values of the parameters. So whatever be the model that you are using, right? So anyway, you have to come up find the values of the parameters. But if you look at this MB model, you can see that this is not automatic. See, we have to solve a system of equations to find the values of the parameters. This is a manual process. You have to do it with a pen and paper. You have to solve you have to derive all these equations. Then you have to solve it, and then you have to come up with the optimal values of the parameters. In this case, you can see that our model is very simple. It takes only 2 inputs, right? So the number of equations will be less. So if your model is taking 100 inputs, so you want to map 100 input to one class, then you will be having more equations, right? Then finding the solution will be more difficult. So this is one drawback of MB model. So this is not an automated model. Manually, we have to find the values of the parameters. Another drawback is this model will work only when the data is linearly separable. If the data is not linearly separable, then the model will not converge. So that means, so you can see an example here. So if you take a AND gate, this is a geometric representation of the working of MB neuron. So in the case of an AND gate, you can see, so these are the output. When both inputs are 0, the output is 0, right? When one is, when B is 1 and A is 0, again it is 0. This unfilled circle means it is 0. When A is 1 and B is 0, again it is 0, right? So in these cases, in these 3 cases, we have the output 0. And when both inputs are 1, we have the output 1. So if you look, these are the outputs, right? So if you look at this representation, you can see we can easily classify these 2 classes with the help of a line, right? So these 3 classes, these 3 values will come in the left side of the line, another will come in the right side of the line. That means this is linearly separable. You can separate the classes with the help of a line. Yeah, so this is linearly separable. Now, if you look at the other case or case, so this also you can see that, see, when at least when one of the input is 1, the output will be 1 in the case of an OR gate. So these are the 4 outputs. So you can see that this case also, we can separate the classes with the help of a line. Right. So in these 2 cases, the data is linearly separable. But if you look at the XOR case, see, in the case of an XOR, the output is 1 when one input is 0 and other input is 1, right? So if you look at this case, you can see that we cannot separate these 2 classes with the help of a line. So that means this is not a linearly separable. So it is not possible to design an XOR gate with a simple MB neuron. So this is one drawback of another drawback of MB neuron. The MB model converges only if the data is linearly separable. If the data is not linearly separable, then the MB model will not converge. The other drawback of MB model is it is not automated. So in 1958, Frank Rosenblatt come up with an idea to automate the model proposed by the MB model. So we will see how the Rosenblatt model will work. So he named his model as a perceptron. So we are going to see how the perceptron work. The concept is again the same. So he made, what he did is he introduced a learning rule to find the optimal values of the parameter. This is only difference between the perceptron and the previous model, the MB model. And he also made a small modification to the mathematical formulation. So if you look at this MB model, you can see this is how the MB model look like, right? First, we have to compute the weighted sum, and based on this weighted sum, we will decide what is the output. If the value is greater than a threshold, we will get 1 as the output. Otherwise, we will get 0 as the output. So he moved this t to the left side of the inequality. Then it becomes sum is equal to sigma is equal to 1 to n IAWA plus b. B is nothing but the minus t. So this t is moved to the left side of the inequality. So then this output look like this, right? Output is equal to 0 if sum less than or equal to 0, and output is equal to 1 if sum greater than 0. So this is the only modification that he did in the to the MB model. So he moved this threshold to the left side of the inequality, and he named it as a bias. And the other contribution was he introduced a learning rule to find the values of the parameters. The learning rule look like. Now again, we are going to design a model, right? So this is how our neuron look like. It takes the inputs associated with every input. There is a weight and there is a threshold. In this case, it is not the threshold, it is the bias, right? So if you want to work with the perceptron, what we do is we can initialize these values randomly. So if you want to design an AND gate with the perceptron, so we have three parameters, right? WA, WB, and T. So these three values we will initialize randomly. So when we initialize these values randomly, and then you can give the input values and see how close the output is to the ground truth. If the output is not close to the ground truth, that means the values that we initialized are not correct. We have to correct the values of the parameters, and that correction is in this case it is doing with the help of a rule called perceptron learning rule, and this is how the perceptron learning rule is described. So now we will initialize all the parameters, the W and B randomly, then we will update it. So Wi plus 1 is the value after the first iteration. So Wi plus 1 is computed as Wi plus delta W, where delta W is computed as eta into error into X, where X is the input and error is the difference between the expected output and the predicted output. So we initialize the model randomly, right? When we initialize the model randomly, we initialize the model randomly and we will give the input. When you give the input and we will see what output we are getting and how close the output is to the ground truth. If there is a difference, that means the parameters, the values of the parameters are not correct. We have to update it. So if the error is not zero, if the error is zero, you can see that W or B is not updated. Otherwise, these W's will update. So this is an iterative approach. The process will continue till the error is very minimum or the error is zero. So this is how the perceptron work. So the perceptron convergence theorem says that the perceptron will converge if the data is linearly separable. So if the other drawback of a MB model is still there. So if the data is not linearly separable, then the perceptron also will not work. But the advantage of perceptron over MP model is that MP model is not an automated one, but perceptron is an automated one. Here we have a learning rule. So you can say that this is a it has all the characteristics of a machine learning algorithm, right? So you have the data with the help of a data, we are finding the optimal values of the parameter, right? So if you want to design an AND gate, then you have to take all the four cases, right? So we will initialize the parameters of the neuron randomly, and we will try to predict the output. So we know what are the expected output. We will compare the predicted output with the expected output, and if there is an error, we will update. We will update the weights using this perceptron rule. So this is how the perceptron look like. Is it clear? So we have n inputs. First, we will compute the weighted sum. This weighted sum we will give to an activation function. As I mentioned earlier, the activation function is again the same, the step activation function. In MB model also they use the step activation function. So we will give to the step activation function and we will get an output. This output you can compare with the expected output, and if the predicted output and the expected output are not same, that means the values of our parameters are not the correct values. So we have to update it. And in perceptron, they use the perceptron learning rule to update the parameters. So now I will discuss an experiment using this perceptron. So what we are going to do is, so this experiment is to highlight some other drawbacks of perceptron. So what we are trying to do is to do a classification of three flowers. So all these flowers belongs to the iris family. This is iris virginica, iris setosa, and iris versicolor. So what we want to do is to classify to which class the flower belongs. Our input is not an image. So if you look at if you observe these flowers, you can see that there is a difference. If you visually analyze these flowers, you can see that it is easy to classify these two flowers. But if you look at this flower and this flower, it is a little bit difficult if we ignore the color. Of course, there is a color difference, but if you look at the sepal length and petal length, it is a little bit difficult to classify, distinguish between these two flowers, the virginica and the versicolor, right? But if you look at the other two cases, it is more easy. So we are going to do this job with the help of a perceptron. So I'm going to use a perceptron to do this classification. So instead of taking this image, I'm going to take some information from this image, like the sepal length and the petal length. So we are considering the petal length and the this sepal length, and we are trying to see whether we can classify these flowers with the help of sepal length and the petal length. So this is the output of these two experiments. So this is output of the first experiment. So these are our input. This is the plot of the input data. And you can see that when we train the perceptron, it come up with a decision boundary. This is the decision boundary that the perceptron generate in the first case. In the first experiment, what we did is we took the data from the flowers belongs to Virginica class and the Setosa class. And here you can see the plot. These are our training data. And once we start training, the model will try to come up with a decision boundary, right? So, and this is the decision boundary that the perceptron generated. So you can see that see, one class is above this decision boundary and other classes belong the decision boundary. That means we can perfectly classify these two classes with the help of a decision boundary. So the model works perfectly. That means whenever the data is linearly separable, in this case, you can see that the data is linearly separable. You can separate these two classes with the help of a line. So here the model worked perfectly. Now we are going to consider the other two classes. So we are considering this Virginica and the versicolor. So if you plot the data, you can see that this is how the plot look like. And you can see that it is not that easy to draw a line to separate these two classes. And this is the decision boundary generated by the perceptron. So you can see that this decision boundary is not a proper one. And with this decision boundary, you cannot classify these two classes. So if the data is not linearly separable, then the perceptron will not converge. That is what you can learn from these two plots, right? But the other drawback of perceptron is, so if you look at this decision boundary generated by perceptron, you can see that it is, even though the data is not linearly separable, it is possible to come up with a better decision boundary. See, if you draw a decision boundary like this, still this line will not separate these two classes properly, but at least the error can be minimized, right? So this is another drawback of perceptron. So the decision boundary generated by perceptron is not a large margin decision boundary. So the margins are small. So since the margins are small, if the data is not linearly separable, the error will be high with the perceptron. So if the data is linearly separable, anyway, the model will converge and you will get a solution to the problem. But if the data is not linearly separable, then the error generated by perceptron will be very high. So this is another drawback of perceptron. So see, if you look at the real world problems, you can see that it is these problems cannot be easily solved with the help of a line, right? You need a very complex decision boundaries. Right. So in those cases, we of course will go with non-linear models. But if you try a perceptron to solve those problems, then the error will be very high with the perceptron. So this is another drawback of perceptron. So to solve these problems of perceptron, Whitrow and Hoff come up with a different model called Adaline. That is what we are going to discuss now. So the difference between perceptron and Adaline is in Adaline they used the gradient descent method to train the neuron. But in the case of a perceptron, we saw that the perceptron uses the perceptron learning rule to develop the model, right? So perceptron learning rule has certain drawbacks. The drawback is it is not having a large margin decision boundary, and because of that, the error will be high when the data is not linearly separable. So first we will see how the gradient descent method work, and then we will see how can we use this gradient descent method to train the neuron. Training a neuron means training a model means we are trying to find the optimal values of the parameter. That is what we are trying to. That is what we do when we say we are training a model. Right. When we train, our model may be having hundreds of parameters or millions of parameters. When we say we are training a model with the help of a training set, we are trying to find the optimal values of the parameters in the model. Right. Okay, so we will see how can we find the values of these parameters with the help of a gradient descent method. So I'll try to explain the gradient descent method with the help of a few graphs in this screen. So I will start with this one. So if you look at this graph, you can see there is a line and you just assume that we are standing somewhere here. And what we want to do is we want to move from this position to this position through the line. So how can we move it? So we had to come up with a formula to move to this point. So this is our target point. And now we are standing somewhere here. So if you look at this line, you can see that this line is having a positive slope. And what we have to do is we have to move against the slope, right? So I'm going to use this formula to do it. So we are going to move against the slope, right? So because the slope is positive. And when we move towards this position, see, we can take small steps or we can take large steps, right? If you take small steps, then it will take time to reach this point. And if you take large step, there is a chance that we may overshoot this point, right? So this is again, you can assume this is step size. You can assume this step size as a hyperparameter. You have to select it based on some kind of heuristics, right? So if you take very small values of this, if you take very small step size, then it will take time for us to reach here. If you take large step size, then you may overshoot it, right? But what we have to do is we have to move against the slope, and we are going to do it with this equation, right? So our current position is x, and the new value is x, and the new value we are computing is x is equal to x plus alpha into m, where m is the slope, and this this alpha is the step size, right? So currently we are here, and you can compute the slope, and we will move against the slope. So based on this step size, we can decide the movement. So if you're taking very small step size, after some time we will reach here, right? If you're taking a large step size, maybe in 2 jumps you can reach here, but that is the risk is associated with it. Sometimes we may overshoot it. Okay, so this is how this movement is defined. Now we will take the other case. We are going to move through this line. So what is the difference between these two paths or these two lines? How these two lines are different?
One is a positive and another one is a negative slope.
Yeah, so in this case, yeah, the slope is negative. But still you can, so in this case, we are moving against the slope. So here we have to move along the slope, right? But still you can use the same equation because our m is negative now. So the equation becomes x is equal to x plus alpha into m, right? So you'll be starting from here and you can decide some step size and finally you will reach here. Okay, now we are going to take a different path. So we are going, instead of moving through the line, we are trying to move through a curve. So we are standing somewhere here and we have to reach here. So what is the difference between these two paths? So how these two paths are different?
It's a curve.
Yeah, this is a curve. So here, if you look at this line, see all points in the line are having the same slope, right? So here the slope is different at different points. How will you compute the slope of a curve? How will you compute the slope of a curve? You can take the derivative, right? So again, I'm going to use the same equation. So see, the slope is computed by taking the derivative, right? Dy by dx, and this dy by dx will be different at a different point. So because the slope will be different at a different points, right? So I'm using the same equation to move from this point to this point. So since I am moving through a curve, I computed the slope by taking the derivative. So my equation becomes x is equal to x minus alpha into dy by dx. So what happens when I reach this point? what happens when I reach this point? You just assume that we are starting from here, right? So we will now my current position is here, right? X, and I will compute the slope. See, the slope is positive, right? So I will again move from, since the slope is positive, it will be x is equal to x plus, I have to move against the slope, x is equal to x minus alpha into dy by dx. So I will reach here. My destination is this point, right? So now again, I compute the slope. I am here, I compute the slope, and in the next movement, again, slope is positive, I reach here. Again, I will compute the slope, I will reach here. So when I reach here, what happens? This is the minimum value, right? When I reach here, what happens to the derivative?
It becomes 0.
It becomes 0. So it becomes x is equal to x minus 0. So x will not update. That means I reached the global minimum, right? So now if you just assume that you're going to use a big value for this alpha, or if you take a bigger value for this step size, so instead of reaching here, maybe in the first jump you may reach here, and in the next jump you may reach here, right? Again, you will be jumping from here to here. So you will keep on jumping. So you may not reach the global minimum at all. So this is the problem with giving a higher value for this step size. Okay. So here what we are trying to find is the value of x that minimizes y, right? So y is a function of x in this case, right? So what value of y minimizes x, right? That is what. So when dy by dx is 0, so we will reach here, right? So now we are going to take a more complex surface. So if you look at this curve, you can see that our y is a function of x. So y depends only on x. Now in this case, you can see that my y depends on x1 and x2, right? And you just assume that we are somewhere here, and we have to reach here, right? So here we try to find the value of y that minimizes x. So here we have to find the value of x1 and x2 that minimizes y, because my y is a function of x1 and x2. So I have to update here. I need to update only x, right? So here I have to update both x1 and x2, right, to reach this point. So what is my x1? X1 is equal to, how I will update x1? X1 is equal to x1 minus alpha into, see, my y is a function of x1 and x2, right? So I have to take, instead of taking the derivative, I have to take the partial derivative, right? So this will be, I have to take the derivative of y with respect to x1. So it will be, I will update x1 like this, right? X1 is equal to x1 minus alpha into dou y by dou x1. And x2 I will update as x2 is equal to x2 minus alpha into dou y by dou x2, right? So after few updates, you can see that we will reach this position. Or you can arrange all these partial derivatives in the form of a vector, and you can call these partial derivatives as the gradient. So this is how the gradient descent method work. So we are trying to find the values of x that minimizes y. So when we have more, when our y depends on more x values, then we have to take the partial derivative, and we have to find what values of those x minimizes y. So when this surface is a convex, then we can make sure that there exists only one global minimum, and our model will always converge to this global minimum, right? But if this surface, if our parametric surface is not convex, then it is again difficult to work with the gradient descent. So if you look at this particular surface, you can see that there exist many minimas, right? So if you look at this one, you can see that this is the global minima, but there are local minimas. So if you start from somewhere here, see, what we want to do is we want to reach this point, but there is always a chance that we may fall in these local minima also, instead of reaching the global minima, right? So what are the characteristics of all these minimas? So what happens to the derivative at this point? Derivative will be 0, right? So what about this point? The derivatives will be 0, right? Dou y by dou x1 and dou y by dou x2 will be 0. So at these local minimas also the derivatives will be 0. So if we fall into these local minimas, then it is very difficult for our algorithm to escape from these local minimas. But of course, there exists some technique to escape from local minimas that we are not going to discuss. But this is one challenge associated with the gradient descent. So if the surface is convex, then our model will always converge to global minima. But if the surface is not convex, then there is a chance that our model will converge to local minima, and as a result, we may get suboptimal results. So this is how the gradient descent method work. I assume, I hope that you got some idea about how the gradient descent method work. Any questions till this point? Okay, so now what we want to do is we want to use this gradient descent method to train a neuron. So training a neuron means we want to find the optimal values of the parameters. So we will see how can we use the gradient descent method to develop a model. So when I say developing a model, we are trying to find a function, right, that maps some inputs to outputs. Finding a function means we have to come up with the optimal values of the parameters of the function, right? So again, I'm going to take a very simple neuron. So this is a neuron that we are going to consider. So this is again a very simple neuron that takes only two inputs. X1 and X2 are the inputs. W1 and W2 are the weight associated with the inputs. W1 is the weight associated with X1, and W2 is the weight associated with the X2. And this is what is happening inside the neuron, right? First, we will compute the weighted sum. So this is how we compute the weighted sum, right? X1 W1 plus X2 W2 plus B. So this A is the weighted sum, and this weighted sum we are going to give to an activation function. So this F is an activation function. So based on this value of A, we will get some Y. And for simplicity, now we are going to assume we are using a linear activation function, or we are going to use an identity function as an activation function. When this F is an identity function, what will be the output? The output will be the input itself, right? So here we assume that this F is an identity function. So in that case, Y will be equal to A, right? So that's all about the neuron. I hope this is clear. So you just look at this neuron. So this is a very simple neuron that takes two inputs, X1 and X2. And W1 and W2 are the weight associated with the neuron. Here we are doing a weighted sum, and this weighted sum we are going to giving to an activation function, and output of the activation function is the output of the neuron, right? So since we are using an identity function as an activation function, the Y will be equal to A. Okay. So now we have to train this model. So train this model means what we are trying to do is to come up with the learning rules. So yeah, so we have to we need some kind of some way to see how close the output is to the the actual output to the predicted output, right? So I'm going to use this error function to check how close the predicted output is to the actual output, right? So you just assume that this Y is the predicted output and T is the ground truth. So we are going to compute the error as T minus Y the whole squared. So when you have multiple inputs, we will take the mean squared error. So so this is how we check how close the predicted output to the actual output. We are going to use the MSE as an error function, and this is the activation function. These two are very important when we work with the gradient descent method. I will explain why this is important, right? So now I explained how our neuron look like, and the activation function that we used is an identity function, and the error function is MSE. This is how we are going to compare we are going to compute the error, or to compare the output of the predicted output with the actual output. Okay. Now we are going to use the gradient descent method to derive a learning rule. Okay, so what we want to do is we want to find what values of W1, W2, and B. These are the parameters, right? W1, W2, and B are the parameters of this neuron or this model. So we want to find what value of W1, W2, and B minimizes the error. This is what we want to find. And I'm going to use the gradient descent method to do it. So this is my updation formula, the weight updation formula. W1 is equal to W1 minus alpha into dou E by dou W1. So this equation means we are trying to find what value of W1 minimizes the error. So this is same as the previous equation. See, this is same. I am using the same equation here. What we did is we tried to find what value of x minimizes the minimizes y. Right? Y is a function of x. Right. So what value of x minimizes y? So the same thing we are doing here. What value of W1 minimizes the error? So this is my weight updation formula. W1 is equal to W1 minus alpha into dou E by dou W1. So now we can simplify this one. So if you take this dou E by dou W1, you can see that the E is a function of y. So you can apply the derivative chain rule here. So dou E by dou W1, you can write as dou E by dou y into dou y by dou W1. Again, you can see that this y is a function of a. So one more time, you can apply the derivative chain rule here. This becomes dou y by dou W1 becomes dou y by dou a into dou a by dou W1. Now we expanded. So what we did is we just expanded this one dou E by dou W1. Now we can substitute the values. You will find dou E by dou y. So dou E by dou y, what is E? T minus y whole squared into half. This half we added just to make the computations much simpler. So E is half of t minus y whole squared. If you take the derivative of this term with respect to y, we will get minus of t minus y. Right. And next is dou y by dou a. So y is equal to a. So dou y by dou a, we will get 1. Now the third time is dou a by dou W1. So we have to take the derivative of a with respect to W1, right? What is a? X1 W1 plus X2 W2 plus B. So there is no W1 in these two terms. So the output will be X, right? So what is dou E by dou W1? We will get minus of T minus Y into X. So if you substitute this value here, we will get a weight updation formula for W1, right? So the new value of W1 will be W1 is equal to W1 plus alpha into T minus Y into X1. Right. So we derived a weight updation formula using the gradient descent method. In a similar way, we can compute for a weight updation formula for W2 and the B. Right. So now we have a weight updation formula, and you can use this weight updation formula to update the weight. Right. Now, if you want to design, see, a neuron that act like an AND gate or an OR gate, you can use this formula. Right, so initialize these values W1, W2, and B randomly, and then we will update these values, and this process will continue till this term becomes a 0. When the predicted output is same as the actual output, this term becomes 0, right? And as a result, W1 or W2 will not update. At that time, the model will stop. That means the model is converged. So this is how ADAR line work. So if you look at, if you compare this ADAR line with perceptron, you can see that in perceptron, Rosenblatt used a perceptron learning rule. That was basically, he took that perceptron learning rule from the book of Hebb. In that book, Hebb described a learning approach. So he used that Hebb's learning rule to train the perceptron. But in ADAR line, Widrow and Hoff, they used the gradient descent method to train the model. So if you observe this slide, you can see that we used this gradient descent method to come up with the weight updation formula. Once these weight updation formulas are there, then you can use these formulas to update the weight. So you have some input. If and when you have the training data, use the training data to develop a model. Developing a model means we have the data, and we are going to use this neuron to develop a model. So we have the data, and we use these training, the weight updation formulas to find the optimal values of the parameters. Once we find the optimal values of these parameters, we can say that this is our model. Right. Is it clear?
Sir,
If
can
you have any questions,
some,
you can ask. Sorry?
Sir, can you quote some real-time examples for this to design this model?
Okay, so you just assume that you want to classify dogs and a cat. So we are going to extract some features of, we are going to use the same neuron. Assume we are going to use the same neuron. Same neuron means only one neuron. So you can, of course, you can build a neural network. A neural network is a collection of neurons. Now we are going to use one simple neuron to classify the input image into dog and a cat. For convenience, you can just assume that our input will be always an image of a cat or a dog. And X1 and X2 are some features. So we are considering only two features, X1 and X2. So these are two features that describe dog and the cat. So when X1 and X2 belongs to, when X1 and X2 are some values or some features of the cat, you just assume that we will get y as 1. And if X1 and X2 are the features of dog, we will get the output as a 0. So this is what we want. So you have to collect the features from n number of dogs and cats. You just assume that we have 50 cats and 50 dogs. So we will be having 100 X1 and X2, right? So we will use these 100 values. So this is again a pair, right? So we will be having 100 pairs, right? So because we have 50 dogs and 50 cats. So we will use these 100 pairs to find the values of W1, W2, and B. Right. So we will give this input. So when we give this X1 and X2, and if this X1 and X2 belongs to the features of the cat, we should get Y as 1. And when these X1 and X2 belongs to the features of a dog, then you should get the output as a 0. So what we are trying to do is what value of W1, W2, and this B make this neuron as a classifier that classify dog and the cat properly. For whatever be these value of X1 and X2, if X1 and X2 belongs to the features of a cat, then we should get output 1. So this is what we are trying to do when we train the model. Is it clear? So, sorry, I was not able to hear you. There is noise in the line.
What will be the value of W1, W2, and B? We have to decide for this.
See, the value of W1 and W2 we have to find, right? So this is the, see, in this case, we want to classify a dog and the cat, right? So, and this is the neuron that we are going to train. So we will initialize W1, W2, and B with some random value. Say this value of W1 is 0.1, say value of W2 is 0.5, and B is say 1. So assume this is the value that we initialized to this to W1, W2, and B. Then we will use this weight updation formula, the weight updation formula that we derived with the help of a gradient descent method. We will use this weight updation formula to find the optimal value. So we start with these values 0.1, 0.5, and B. So this is again we are assigning random values. With this, from this random value, we will update the value of W1, W2, and B. When your model converges, or when your model learned the features of a cat and the dog, then it stops updating the weight. So that value of W1 and W2, B are the optimal values of the parameters. If you use that trained values of W1, W2, and B, then you can use this neuron to classify dog and the cat. With the help of this gradient descent method, this is what we are trying to find, right?
Everything we have to compute, sir, for that.
Sorry.
Everything is we have to manually calculate all these things.
No, we are not manually calculating. So this is an iterative approach, right? We are not manually calculating anything. So this is the formula. So I have a formula to update W1. I have a formula to update W2, or I have a formula to update B. What I am doing is I'm just initializing W1, W2, and B randomly, and I have input. I have 100 pairs, right? I am giving this input, and all these updations are happening automatically. And if this cat and the dog, if you can classify it with the help of if it is linearly separable, then in the end, after few iterations, the model will come up with the optimal values of W1, W2, and B. Then the training will stop. There is no manual intervention here.
You have to design some program for that. Can you say?
No, what you are designing is only the neural network. You have to design the you have to design the model, right? So in this case, we are considering only one neuron. So we are telling the algorithm that, see, I have only one neuron. I want this one neuron to classify dog and the cat. But sometimes with one neuron, it is not possible. So if with one neuron, if your model is not at all converging, then you have to use a neural network. You can use a combination of 3 or 4 neurons to achieve the task.
Excuse me, sir.
Oh.
Sir, is there a way to know that whether a function is convex or non-convex?
Yeah, if a function is convex, then we have only one. You can plot that function.
Okay.
If it is convex, then there will be only one minima, right? If it is not convex,
We will have many.
yeah.
Okay,
But
that is through plotting we can find and then go for whether it is suitable for GD or not.
yeah, but we don't know how our error surface look like, right? Our error surface in practice, our error surface will not be convex at all. It will be a very complex surface.
Okay.
If it
So
is
it is
always
through
convex, yeah, if it is
trial
always
and error, we find like if we apply GD or this neural network model, and sometimes it might have multiple local minima also.
if
You
it
may
has
not.
multiple local minimas, and then what happens is if you repeat the experiment, you may get different results. But there are other ways. There are ways to escape from local minimas. There are different optimizations. You can there are ways to improve the performance of gradient descent. For example, instead of using a normal gradient descent, you can use stochastic gradient descent. Stochastic gradient descent with the other method. There
But
are
how
different
will no,
optimizations.
sir? But that is like when I find that there is many local minima. But how will I identify like I have ended up with a multiple local minima problem, so that I can opt for other algorithms?
No, in practice, it will not be a convex. If you look at the error surface, there are some ways to see how the error surface look like. So if you look at the error surface, it will never be convex. So our function, our y is a function of millions of parameters, right? And this surface is so complex, it will never be a convex.
Okay.
So there is always a chance that the solution that you are getting is suboptimal, but there are ways to
Improve it.
improve it.
Okay. Okay, sir. Thank you.
Any other questions? Okay, so we'll go to the next slide. So yeah, so now I assume that you have some idea about Adaline and perceptron. So one difference between Adaline, both Adaline and perceptron, if you compare Adaline and perceptron, you can see that both models, if you develop a model with the perceptron or if you develop a model with Adaline, both model learns from the data. But and these models will converge only if the data is linearly separable. But one difference is in the case of an Adaline, the margin is large when compared to perceptron, and as a result, if the see this is what we discussed about margin, right? So if in the case of an Adaline, it will come up with a better margin when compared to perceptron. So what happens is even if your data is not, if your data is linearly separable, you will get a solution with both perceptron and Adaline. But if your data is not linearly separable, both perceptron and Adaline will not converge, but the error will be less with the Adaline when compared to perceptron. This is one advantage of perceptron over, this is one advantage of Adaline over perceptron. But again, if you want to use the gradient descent, see, make sure that your error function and the activation function is differentiable. If your error function and activation function is not differentiable, then the gradient descent will not work. So you can use, here we use the MSE as the error function and identity function as an activation function. This is differentiable. So if you're not able to take the derivative of error, these two terms, then it is very difficult to come up with a weight updation formula using gradient descent. So make sure that this is differentiable. So you can see that in the case of perceptron, they use a step activation function, which is not differentiable. So we cannot use step function as an activation function with ADA line. Um, See, the one thing that is common with the perceptron and ADA line is it works only if the data is linearly separable. But in practice or the real world problems, we cannot come up with a solution with a linear classifier. See, the linear classifier works if you can separate the classes with the help of a line. But in practice, it is very difficult to get data like this. So most of the problems that we want to solve with our machine learning models are not linearly separable. So if the plot of the data is something like this, see, you cannot simply come up with a line to classify it, right? So here you cannot classify these two classes with a line. You need a complex non-linear decision surface. So how can we develop a non-linear model? So how can we develop models that can use a non-linear decision boundary to solve the problem? So that we will see. How can we use our neuron to or a neural network to solve the data that is not linearly separable. So what you can do in the case of a neural network is, so if you look at this ADA line, we saw that we used an identity function as an activation function, right? That is a linear activation function. So if you want to work with data that is not linearly separable, what you can do is use nonlinear activation functions in your neuron, right? If you create a neural network with a nonlinear activation functions, then our classifier will become a nonlinear classifier, and you will be able to come up with a nonlinear decision boundaries that will help us to classify the data that is not linearly separable. And one of the most commonly used nonlinear activation function is the sigmoid activation function. So here you can see the definition of the sigmoid function. This is how the sigmoid is defined. Y is equal to 1 plus 1 divided by e raised to minus x, where x is the input and y is the output. And this is the shape of the sigmoid function. So it has an S-shaped. You can see that this is, we will get an S-shaped curve. When the value of x tends to infinity, y tends to 1. You can see it here. When the value of x tends to minus infinity, y tends to 0. So you can see that the sigmoid function is bounded. That means the output will be always 0. Output will be always between 0 and 1. This is one beauty of a sigmoid function. And if you want to use sigmoid function with a gradient descent, we want to make sure that sigmoid function is differentiable. You can see that the sigmoid is differentiable. So if y is a sigmoid function, then the derivative will be y into 1 minus y. So these two characteristics of sigmoid enables that function to use it in a neural network. So output is bounded. That is very important. See, if you are going to do some kind of prediction with a linear activation function, then the output will not be bounded, right? If you are getting an output between, say, minus infinity to infinity, it will be very difficult for you to classify after training. If you're getting an output between minus infinity to infinity, it will be very difficult for you to map the output to some classes. And you just assume that we are using a sigmoid function. In that case, output will be always between the 0 and 1. The prediction will be between 0 and 1. There you can set a threshold as 0.5. Say if the value is above 0.5, then we can map it to class 1. If the value is below 0.5, we can map it to the other class, the 0 class, right? So this is advantage of a bounded function. So sigmoid is bounded. Value is always between 0 and 1, and sigmoid is differentiable. So here you can see the plot of sigmoid function and its derivative. This is a sigmoid function, and this is the derivative of the sigmoid function. If you carefully observe, you can see that the derivative value for sigmoid is very small. So this is one drawback of the sigmoid function. Okay, so sigmoid is a nonlinear activation function, and now we will see how can we incorporate sigmoid function into the neuron. So again, I'm going to take the same neuron, and what I want to do is I want to make this neuron a non-linear neuron instead of a linear neuron. For that, what I did is I am going to use the sigmoid function as an activation function. Everything else is same. X1 and X2 are the inputs. W1 and W2 are the weight associated with X1 and X2. So here we are computing the weighted sum, and this weighted sum is given to a sigmoid activation function. Output is y. y is the output of the sigmoid activation function. Earlier in the previous case, what we did is we used an identity function. In that case, y was equal to a, right? Here, y is sigma of y. So here we are going to use a sigmoid activation function. Okay. So again, we are going to derive the weight updation formulas. Everything is same here. All these things are same. The only difference is, so this is again the same. This is same. So in the previous case, since we used an identity function, this value was 1. Now this is different, right? So here we are using a sigmoid activation function. We are taking the derivative of the sigmoid, and as a result, we will get y into 1 minus y. So now we will get again we will get a weight updation formula. So this is the weight updation formula that we derived. The only difference between the previous neuron and this neuron is the activation function. So earlier it was 1. Now if we take the derivative, you can see that y into 1 minus y, right? So you can use this weight update rule to train the neuron, right? So that is why I told. See, if you can use any activation function or any error function. So when you use different activation functions, you have to make sure that the activation function and error functions are differentiable. So now this is the weight updation formula that we got. So again, the same thing. If you want to train this particular neuron for some purpose, and if you are using this sigmoid function, you can use this weight updation formula to train the model, right? Okay, so if you carefully observe these formulas, you can see that there is this y into 1 minus y is the derivative of the sigmoid. And if you observe this derivative of the sigmoid, you can see that these values are very small. So one problem with sigmoid neurons is sigmoid neurons are very slow. Very slow means it learns very slow, and that is mainly because the derivative of the sigmoid neurons are small. And as a result, the weight updation will be very small. This is one drawback of a sigmoid. Sigmoid has many interesting properties, but one drawback is since the derivative of sigmoid is small, sigmoid neurons learns very slow. And if you create a network with the sigmoid neurons, and there is also a you can also face this gradient vanishing problem, because if you use a network of neurons, and this gradient has to propagate back. So when this gradient is very small, at some point of time, it can be very close to 0, and as a result, our model will not learn at all. So these are some of the drawback with the sigmoid neurons. So we will see what are the other commonly used activation functions. Other commonly used activation functions are TANH and ReLU. So this is how the TANH is defined, and this is how the ReLU is defined. So TANH y is equal to e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. So the difference between the similarities between sigmoid and TANH is both sigmoid and a TANH are bounded. In the case of sigmoid, the value is between 0 and 1. For TANH, it is always between -1 and 1. So one advantage of TANH over sigmoid is TANH is zero-sunded, but sigmoid is not a zero-sunded. Since TANH is zero-sunded, see the gradient can move in both directions, positive and negative direction, and as a result, TANH neuron can converge faster than sigmoid neuron. The other advantage of TANH over sigmoid is the derivative of TANH is higher than the derivative of sigmoid, and as a result, TANH neurons learns faster than sigmoid neurons. Now, if you look at ReLU, this is how ReLU is defined. Y is equal to max of 0, x. If the value of x is greater than 0, the output will be x. Otherwise, it will be 0. Right. So, if you take the derivative of ReLU, you can see that whenever the value of x is greater than 0, the output, the derivative will be 1. So that means the derivative of ReLU is higher than the derivative of sigmoid and TANH. So here you can see the plots of the different activities. So if you look at the literature, you can see that other commonly used activation functions are TANH and ReLU. So if you compare, so this is how the sigmoid is defined, and this is how the TANH is defined, right? So if you compare sigmoid and TANH, you can see that see in the case of sigmoid is bounded. The values are between 0 and 1, and in the case of TANH, the output is between -1 and 1. So both sigmoid and tanh are bounded, but if you look at a tanh, you can see that tanh is a zero-sunded. So if you look at tanh, you can see that tanh is zero-sunded. So the advantage of zero-sunded functions is that see the derivative can move in both directions, positive and negative directions. So if you use tanh, then your tanh neuron can learn faster than sigmoid neuron because the tanh is zero-sunded. The other advantage of tanh is the derivative of tanh is higher than the derivative of sigmoid. So tanh neurons learns faster than sigmoid neuron. So the other commonly used activation function is ReLU. So this is how the ReLU is defined. Y is equal to max of 0, x. So the output, if x is greater than 0, the output will be x itself, right? So if you look at ReLU, you can see that the ReLU is not zero-sunded, but the derivative of ReLU is much higher than the derivative of sigmoid and tanh. So here you can see the comparison of the derivatives of different activation functions. This is the derivative of ReLU. You can see that the derivative of ReLU is higher than the derivative of sigmoid or tanh. So if you use ReLU as an activation function in your neuron, then your model will learn much faster when compared to tanh neurons or sigmoid neuron. So here you can see an experiment described in the AlexNet paper. So they did an experiment with this CIFAR data, I think. So this is the plot. So you can see that here you can see two plots. One corresponds to tanh and one corresponds to ReLU. So when they use tanh as an activation function to develop their model, so it took almost 36 iterations to converge. So when they use ReLU activation function, their model converged in 6 iterations. So in their paper, they say that see the ReLU is almost 6 times faster when compared to tanh and many times faster than sigmoid. So this is very important, right? This is why see this ReLU was introduced somewhere in 2005 or 2006. Before that people used tanh or sigmoid to develop neural networks. So at that time, see, the training was very difficult. So they used a neural network only to work with the small problems. So for very complex problems, the problem with a neural network was you have to wait for a long time to get the result, or you use a very, you also need a very complex hardwares to get the result, very powerful hardwares to get the result. So this was not available in 1990s or 2000. So even though this convolutional neural networks were proposed in 1990s, it was not popular. So SVMs or random forestry or other architectures, other machine learning methods were more popular when compared to CNNs or ANNs. This was one of the reasons. Training a neural network was very slow. That was mainly because of the activation functions used in the neuron. So when ReLU was introduced, the training becomes much faster. And as a result, a neural network also become much popular. So this 6 times is very important, right? So if you use a tanh and if your model is taking 6 days to train, with a ReLU, you can train the same model in 1 day. So that makes a difference. That makes the neural network also very popular. So, but as I told, one the limitation of ReLU is the output is not bounded. So usually what people do is they use ReLU activation functions in the hidden layers, and they use sigmoid activation function in the output layer when they develop a neural network. Okay, I'll try to finish it in another 5 minutes. See, till now we discussed only, hello?
Doubt, sir. You said
Yes.
this activation function has a role on deciding the computation time. Do they have any impact on the accuracy of the model?
The accuracy again, so we have to see how it depends on the accuracy. See, when we use a neural network to design a model, we are trying to map some kind of input to the output, right? So that doesn't make much difference. So in the end, see, when we train the model, we are trying to come up with some kind of optimal values. So whether it has any influence on the accuracy we have to see. We have to try with the different activation functions, and we have to see. But if you are using a sigmoid or a tanh activation functions, in most of the cases, even your model will not converge. So accuracy doesn't make much sense there, right? We don't know whether a model with a sigmoid gives a better result when compared to ReLU. But if you build a very big neural network, say for most of the complex problems, usually there will be hundreds of layers. So you cannot build a neural network with hundreds of layers with a sigmoid or a tanh hidden neurons. So that is very challenging. Your model may not train at all. But the performance again, yeah. So which activation function to use is again a hyperparameter. So I don't know which one will give you the best result. You have to try with the different activation functions. But even developing such a complex model on a complex data with a sigmoid or a tanh as a hidden layer, that doesn't that may not work at all. But for the small problems on a small network, you can try. You can design a neural network with a different activation functions and see which one is working properly. So what influence of accuracy? I don't know exactly what influence it will make on the accuracy. Yeah, but you will not be able to design a very complex neural network with sigmoid or tanh activation functions.
Yes, sir. Got it, sir. Thank you.
So for small dataset or with the small networks, you can try with a different activation, sigmoid, tanh or ReLU. But if you want to build a very complex network, then yeah, as I told, it will be very difficult with other two activation functions. Yeah, using which activation function to use is again a hyperparameter, like how many layers you need and all. Okay, so till now we discussed about we discussed a neural network with just only one neuron. So with just one neuron, we will not be able to design a very. We will not be able to solve very complex problems. So if you want to solve very complex problems, then you have to design a neural network. A neural network is a collection of different neurons and layers, right? So we will see how to design a neural network. And what are the challenges associated with it? So if you look at this model, so you can see here we have two layers, right? So we have input, we have the input layer, we have one hidden layer, and we have an output layer, right? In the output layer, we have one neuron, and in the hidden layer, we have two neurons, right? So now we know how to derive the weight updation formula. So if you look at if you take this particular neuron, we can see that it is easy to come up with a weight updation formula. You can find a weight updation formula for W5 and W6. This is very easy because we know what is expected output, right? Output of this neuron is the output of the neural network. So this neuron will predict some values, and we know what is expected value. So you can compute the error. So what about the expected value at these 2 points? So here we don't know what are the expected values, right? So then how we will find the weight updation formulas for W1, W2, W3, and W4. So this is the question. So what you can do here is, again, you can use the derivative chain rule to solve this problem. So here you can see a neural a network with two hidden layers and one output layer. So we have some input, and this input is connected to this neuron. W1 is the weight associated with it. This hidden one is this neuron. This is connected to this one, and this is connected to this one. So when we design a neural network with different layers and with multiple neurons, what we are trying to find is what values of the parameters minimizes the error. So in this case, see, we want to see what value of W1 minimizes the error. So to do it, what we do is we have to take the partial derivative, right? Dou error by dou W1. So dou error is the error, and W1 is this variable, right? So we want to find what value of W1 minimizes the error. So here you can apply the derivative chain rule. So if you look at this derivative chain rule, you can see this is dou error by dou output into dou output by dou hidden 2 into dou hidden 2 by dou hidden 1 into dou hidden 1 by dou W1. So when so you can see here we have 4 terms. When the number of layers increases, then the number of terms in this equation also will increase. So here, if you just assume that when these derivative values are very small, then what happens is when you do this multiplication, it becomes very close to 0. This is one problem associated with a sigmoid neuron. This is called the vanishing gradient problem. So if you use sigmoid neurons in these hidden neurons, there's a chance that our model may not converge, because when these values become very close to 0, what happens is the weight will not update, right? That means the model will not learn. So for W2 also, so if you want to find dou error by dou W2, then the number of terms in this weight updation formula will be less. Right. So you can apply the derivative chain rule when we have derivative chain rule to derive the weight updation formula when we have multiple layers and multiple neurons. So this is how the backpropagation algorithm work. So you can use this derivative chain rule to train a neural network. This is similar to how we derive the weight rule to derive the weight updation formula to train a single neuron. So what we do is I'm skipping all these portions because we don't have time. And I will briefly explain how this backpropagation work. So see, instead of a neuron, now we assume that we have a neural network. Our neural network has different layers, right? Different layers, and every layer you just assume that we have multiple neurons, and the weights, everything is there. So we will give some input, and before giving the input, what we are going to do is we are randomly assigning some values to the parameters of this model. We will give some input. So for every neuron in every layer, we will get some output, and in the end, we will get an output for the output of the model, right? So when we get the output, so of course we will be using some loss function to see how close the output is to the actual the predicted output to the actual output. If there is an error, you can use any loss function. Say it can be the cross entropy or MSE or whatever be it. So when there is an error, that means the values that we used are not optimal, and we have to update it. And to update those parameters, we again use the weight updation formula. So this based on this error, what we do is see, based on this error, we will update every parameter. Say error with respect to dou W1. So once we have dou error by dou W1, we can easily update W1. W1 is equal to W1 minus dou error by dou W1, right? So we will get a weight updation formula for W1. In a similar way, we will update the values of all these parameters. After updating these values, again we will predict the output and see what error we are getting. So naturally, if the model is learning, you can see that the error will come down after every iteration. So if the error is still there, again we will update based on this updation formula, and again we will continue this process till the model converges. So if your model is actually learning, you can see that the error is coming down. If the error is not coming down, that means your model is not learning. Your model may be too simple, right? So you want to increase the complexity. You can add more layers and make the model more complex. Again, you have to do this process. So this is how we develop the model. And this is how the backpropagation algorithm work. When you develop the model, make sure that the model is not overfitting and the model is not underfitting. So I'll just explain, I'll briefly explain the terminologies overfitting and underfitting. So underfitting means the model is too simple. It is not learning anything. So you can look at this figure. So you just assume that, this is this is the plot. I have a plot. This green is my function, and I'm going to take some samples from this green plot. These blue dots are the samples I took from this green plot, and I'm going to use these dots as my training sample, right? But this is the data that I have, the blue dots, but I'm going to use a very simple function, right? In this case, a polynomial of degree 1, and this is the output that I got. So you can see that this is what I got, and this is what I am expecting, the green curve, right? So see here, the problem is I used a very simple function to do the prediction, and as a result, the model is not learning. So this is same with the neural network also. So you may want to solve very complex problem, say face recognition or some kind of classification. But if your model is very simple, then the model will not learn. In that case, you can say that my model is underfitting. So this is what is underfitting. So when your model is underfitting, what we do is you can increase the complexity. So when you increase the complexity, here you can see that instead of using a polynomial of degree 1, I use a polynomial of degree 4, and this is fitting properly. Oh, when I see that this is fitting properly, I again increase the complexity. Yeah. So yeah, I was trying to explain this overfitting and underfitting with a simple example. So underfitting means the model is not learning. So if you look at this figure, see, you can see that, see, we want to learn this green curve. And what we are going to do is we are trying to take some samples from this green curve. And we are trying to develop a model that generates this green curve. So what happened here is I used a polynomial of degree 1 to develop the model. And this is what I got, this blue one. So here you can see that this is underfitting. So this is underfitting because my model is too simple. So this is same with the neural network also. So if you want to develop a model to identify face or to classify this handwritten digits. So with one neuron or with a very simple model, the model may not learn. So if your model is underfitting, then what is the solution is to increase the complexity. So increasing the complexity means you can increase, you can add more layers. You can also add more neurons in every layer. This will increase the complexity of the model. So here you can see an example. So from degree 1, here I went to degree 4. So when I increase the complexity, you can see that the curve that the model generate is fitting the true function properly. By seeing it, I again increase the complexity. When I again increase the complexity, you can see that my model is fitting the trained data very well. But this is not what I want. I want the green one, right? So this is called overfitting. So what happens is when you increase the complexity too much, your model will give very good results on the trained data. So when we develop a model, we will be having trained data and test data, right? What is the purpose of trained data? What is the role of trained data?
To train the neural network and to update the weights.
What do you mean by training the neural network?
We are feeding the input features, sir, through the training data.
And we are training means we are developing a model, right? We are trying to find the optimal values.
Yes.
And for that, we use the trained data. So how will you check whether your model is learning the trained data?
If the error is minimum, then we can check that with the trained data we are getting.
Which error you are talking about? Train error, right?
Train error, sir. Yes.
So when you develop the model, you just observe the train error. As iteration improves, and if your train error is coming down, that means your model is learning, right? So you just assume that you start with a simple model and the train error is very high. So what you did is you increase the complexity of the model, you added more layers, more neuron, and as a result, the train error is very less. So now the train error is very less. You developed a model, right? Now I have a model with a less train error. So whether that is enough to develop a model? Why you need a test data?
It may fail for the new values. That's why.
Yeah. So see, even though both the train and the test error come from the same population, so there can be some noise and all, right? So you just assume that your train data is little bit noise, and overtraining means your model will now try to learn the characteristics of the noise also. And as a result, the model performs very good on the train data, and the performance on the test data might not be that good. So in that case, we will say that the model is overfitting. So when you develop a model, make sure that the model is not underfitting and the model is not overfitting. In that case, we can say that the model is generalizable. So we need good performance on both the trained data and test data. When the model is overfitting, underfitting, the performance of the trained data will be poor and the performance on the test data will be poor. When the model is overfitting, the performance on the trained data will be very good, but the performance on the test data will be poor. So you don't need to make the model very complex, and it should not be too simple. It should be somewhere in between. So when you say that the model is generalizable, the training error will not be very close to zero. There will be some training error, but the test error will be acceptable. So when you develop a model, that is why we need both train data and the test data. So we use train data and test data to decide what should be the complexity of the model. So if you use only the train data, then we will not be able to make sure that the model is generalizable or not.